Okay, in this video, I want to talk about valence shell electron pair repulsion theory. We have talked about this theory in the class, so here I just review a basic concepts for that, and then I will do some example based on the Lewis structure that we have already drawn in the class. So what valence shell electron pair repulsion says? It says if you have the electron pairs or the electron domains around the central atom, they repel each other. So they orientated as far as possible from each other to minimize the repulsion between these domains. So, for example, suppose you have these molecule. So this molecule has two domains. One domain is here, the second domain is here. So these domains repel each other. So the best position for them to minimize the repulsion is when they form 180 degrees relative to each other, or when they are exactly opposite to each other. So it's very important to know how many domains do you have in the molecule. The domain I write here, the domain includes the number of bonds around the central atom plus the number of lone pairs lone lone pairs which you have around the central atom. For example, look at this molecule, the ammonia. This is the Lewis structure for the ammonia. So let's find the domain of the ammonia. The domain of the ammonia, you have one, two, three, four domains around the ammonia molecule. Three of them are bonds plus one of them which is lone pair. So totally you have four domains around the nitrogen or central atom in the ammonia molecule. So the domains are area which you have electron in that. That's why we say the domain repel each other, because the electrons are negative, and you know that negative charge repels each other. So let's have another example. The water molecule. This is the Lewis structure for the water molecule. If we want to find the domain of the water molecule, this is 1, 2, 3, 4. So you have four domains around water molecule. Two of them are single bonds plus two lone pairs. So totally you have four domains. The next example is carbon dioxide, CO2. This is the Lewis structure for the carbon dioxide. So let's find the amount of the domain that we have here. Here around the carbon dioxide you have only two domains. One domain is here, the second domain is here. So you have two bonds. Both of them are the double bonds. So no matter if you have single bond, double bond, or triple bond, all of them count one. Plus you don't have any lone pair on the central atom. So total domain in CO2 molecule is 2. So you can see that you have a lone pair here around the oxygen, but as we said, the domains in the domain we only count the lone pair which you have on the central atom. So these lone pairs is not count as the domain. Okay, so let's move on. So here I write the domain which relates to the hybridization which is available in the molecule. Hybridization. If you have two domains, the hybridization is sp. It means one s orbital and one p orbitals are mixed with each other, and it has made two new domains, or we can say two new hybrid orbitals, which the name of each one of them is sp. So when you have two domains, the best arrangement for the molecule is linear. So the two domain forms 180 degrees relative to each other, because if the two domains are opposite to each other, they have minimum repulsion between them. If you have three domains, the hybridization is sp2. It means one s orbital and two p orbitals are mixed with each other, and they have made three new domains or three new hybrid orbitals, which the name of each one of them is sp2. If you have three domains, the best arrangement for them is like this. So this structure is called trigonal planar, because all of these three domains that you have here around the central atom is on a single plane. So that's why we call it trigonal planar. This arrangement is called linear that we had earlier. In the trigonal planar, the angle between the domains are 120 degrees. So we call it trigonal because it's trigonal and it's planar because all of these bonds or domains are on the single plane. Okay, if you have four domains, the hybridization would be sp3. It means one s and three p orbitals are mixed with each other. They form four new orbitals, or four new domains. So for these four new orbitals, the best arrangement is tetrahedral. The tetrahedral arrangement is three-dimensional. So these two bonds that you can see here, or these two domains, are on the plane. This one is coming out of the plane, this one goes inside the plane. So we draw it three-dimensionally. The angle between all of these domains are 100.5 degrees. This arrangement is called tetrahedral. Okay, now if you have five domains, the hybridization is sp3d. One s orbital, three p orbitals, and one d orbitals are mixed with each other. So they form five new hybrid orbitals, which the name of each one of them is sp3d. So you can see that the number of the hybrid orbitals which forms, or the number of the domains, is equal to the number of the atomic orbitals which are hybrid with each other. So here you have one s orbital, three p orbitals, and one d orbital. So totally five atomic orbitals are mixing with each other. So that's why they are making five domains, or five the new orbitals, which the name of each one of them are sp3d. So you have five orbitals, which the name of each one of them is sp3d. So the number of the hybrid orbitals which forms is same as the number of the atomic orbitals which are mixing with each other. Okay, so for five hybrid orbitals or five domain, the best arrangement is as this. So you have one domain at the top, one domain at the bottom, one domain at the right, and one domain is coming out of the board, one domain is going into the plane or into the board or the surface that you are drawing on that. So you can see at the middle you have a plane. It's like the trigonal planar plane, but at the top of that you have one domain here, okay, and one domain is at the bottom of this plate, this plane. So let's talk about the angles. The angles that you have between these domains in the plane, which is at the center of the molecule, is 120 degrees. Okay, so this one same as this trigonal planar. So at the center you have a trigonal planar arrangement here. Okay, and the angle between these domains at the top and each one of these domains that you have in the plane is 90 degrees. So same thing here, 90 degrees. Same thing for the domain that is at the bottom of the molecule. The angle between this domain at the bottom of the molecule and each one of these domain in the plane is 90 degrees. Okay, between this one and this one, the angle is 90 degrees. Okay, so you have one more angle, and that is between these two domains which are opposite to each other. Okay, so between these two domains, the angle is 180 degrees. So you have three angles in this arrangement. So one angle is 90 degrees, 120 degrees, and 180 degrees. So you have three angles here. This arrangement is called trigonal bipyramidal. So we say trigonal because it's like the trigonal, you have a trigonal arrangement here at the center. We call it pyramidal because you have actually two pyramid here. Okay, one is here at the top. So this is one pyramid at the top, and you have one more pyramid here. So you have one pyramid at the top, one pyramid at the bottom. That's why we call it trigonal bipyramidal. Okay, so let's go to the last one. When you have 6 domains, the hybridization is sp3d2. One s orbital, 3p orbitals, and 2d orbitals are mixed with each other, and they have made 6 new hybrid orbitals. So for 6 domain, the best arrangement is like this. So one domain at the top, one domain at the bottom. 2 of the domains is coming out of the board or the plane that you are drawing on that, and one domain is going inside. Okay, the angle between all of them are 90 degrees. So you have 90 degrees here, you have 90 degrees between this one, and this one is 90 degrees. So all of these angles are 90 degrees. Actually here you have a plane at the center. Okay, one domain is going right up, and one domain is here at the bottom. So this arrangement is called octahedral. Okay, now we have just reviewed the valence shell electron pair repulsion theory, and we talk a little bit about the geometry of these domains that we have. Now let's go and draw the shape of the molecules for the Lewis structures that we have already drawn in the class, and let's talk about their shape and the angles on those molecules.